Welcome to this session, and today we are going to discuss the question bank of the second module, relations, functions and lattices. So now, many to one function. See here, there are some of the functions we are going to define as a function f from a to b is said to be many to one if and only if two or more elements of A have the same image in B. Two or more elements in A will have the same image in B, then we can say that such a function is a many one function. Suppose here f of x is equals to x square is a function f of x and it's a function. So for every is a function defined from a real number to real number, then that means for every, let us say, if I am taking f of minus 1 is equals to 1 and f of plus 1 is equal to 1. So if I am taking the real number, let us say r, then what I am going to take the numbers, let us say minus 1, 1, minus 2, 2 and minus 3, 3. Like that it will move, and here it is going to map to more than one element. Minus 1 and 1 is mapped to 2, and then this is minus 2, 2 is mapped to 4, and next minus 3, and next plus 3 is mapped to 9. So such a function we are calling it as a many one function. Now let us say what is the into function and what is onto function. So a function is f from a to b is said to be into function if there exists at least one element b belongs to b, one element b belongs to b, which is not having a pre-image, So then such function is known as a into function. So otherwise it is onto function. That means every element in B belongs to B which is having a pre-image, then that is known as a onto function. Suppose if I am going to consider, let us say A, B are two sets and F is a function. Now we have to verify whether this function is a one onto function or into function. Let us go for, I am taking A, B, C, D, E. And the next 1, 2, 3, 4. This is A and this is B. Now A is mapped to 1 and B is mapped to 1, C is mapped to 4 and D is mapped to 2 and E is mapped to 3. See here, for each and every element of B belongs to B, every element of B belongs to B, then it is having a pre-image, or else we can say that every element is mapped with some element of A. So this is known as a onto function. So here let us say the another one is A is second one is, let us say A is related to 1, B is related to 3 and C is related to 4. So here element 2 will not have a pre-image. So this is not onto. And of course this is into function. And then another one is when a function f is onto, and then it is nothing but from A to B, and we can say that a onto function is also called as a surjective function. So this is let us go for, this is another function defined from A to B, and here there are some more functions will be there. What is a one function and what is a onto function, what is a constant function. There are some more functions are there. We are going to discuss one after the other. So a function, when we say that a function is one to one, a function is one-to-one or injective function, and if different elements of A have the different images of B under F, then we can say that that function is 1 to 1. Or whenever any two elements x1 comma x2 belongs to A, such that f of x1 is equal to f of x2 implies, that means we are going to take two elements in the set A, then the images, whenever the images are equal, then we can say that the elements are also equal, the elements are equal, or we can say that if x1 is not equal to x2, then f of x1 is not equal to f of x2, we can say that the function is 1, 1. Or simply, this is mathematically, whenever if you are going to prove any functions given in terms of equations, then we are going to apply this. And here, otherwise we are going to use this, different elements will have different images, different elements of A will have different images in B under F, then we can say that it is a 1, 1. It is a 1, 1. Then the another one is identity function. See, a function f is from set A to itself, then f of A is equal to A, then we can say that it is an identity function. Let us say I am just saying that A is 1, 2, 3, and then B is also A is 1, 2, 3 defined in A to A, then f of 1 is equal to 1, f of 2 is equal to 2, f of 3 is equal to 3, then such function is known as a identity function. Identity function. Of course, we can say that identity function is also denoted by IA. That means identity function defined on the set A. Then constant function. Then f is from A to B. A to B. A is 1, 2, 3. And next B is, let us say ABC. ABC. So, for every f of 1 is equal to C, f of 2 is equal to C, f of 3 is equal to C, then we say that the function is a constant function. For every value of A belongs to A, it is maps to only one element. So such function is known as a identity function, constant function. So here A is equal to this, B is equal to this, and the function is defined as, then, so here it is given as A, B, C, D, E. And next another one is B. 1, 2, 3, 4, 5, 6. So A is 1, and next B is 6, and next C is 2, and D is 3, D is 3, and E is 4. So here you observe this, every element A belongs to A will have different elements, maps, different images. So we can say that it is a one function. And of course, it is not onto, because 5 is not having a pre-image. It is 1, 1, but it is not onto, but it is into function. Into function. Then the another one is, it is given as the function, let us say, the set A is defined as 1, 2, 3, 4. A is 1, 2, 3, 4. And next another one is B as A, B, C, D. F of 1 is A, and next 2 is A, and next 3 is D, and 4 is C. So if you observe this, it is 1, 1 or not. So here 1 and 2. So f of 1 is equals to f of 2 is equal to A, but they are equal, the images are equal, but 1 is not equal to 2. So we can say that the function is not 1, 1. Is not 1, 1. Now, 1 to 1 and onto function. A function which is 1, 1 and onto, it is known as a bisection function. And invertible function, another one is, a function is said to be invertible if f inverse is also a function. F inverse is also a function. Or else we can say that f a function is said to be invertible if it is 1, 1 and onto. If it is a 1, 1 and onto. So f is, it is given, and if you are going to find, suppose f is an invertible function, then f inverse, we are going to find f inverse as like this. So just simply, it is going to be reversed. So f is a mapping from A to B, A to B. If it is 1, 1 and onto, then f inverse is mapped from B to A. F inverse is mapped from B to A. So here, like this is a invertible function. And next, another main concept will be a partially different partial order relation. A relation is said to be a partially ordered if it satisfies these properties. One is reflexive, antisymmetric, and transitive. Whenever a relation is satisfying all the three properties, then the relation is known as a partial order relation. Partial order relation. So here let us consider first the most familiar partial order relation is less than or equal to, defined on the set of integers, then that is known as less than or equal to, which is reflexive as well as antisymmetric and transitive. So we can say that the reflexive, the less than or equal to relation is known as a partial order relation, and defined where the set is. That means it is defined on the set of integers. So the Z, we are going to call it as Z comma, and the relation which is known as a partially ordered set. So let us go for with some examples. Let us go for A is this and R is this, and we are going to verify whether it is a partially ordered relation or not. So for that, first of all, it should be reflexive. Now 1 if I am taking 1 is there, 2 if I am taking 2 is there, 3 if I am taking 3 is there, 4 if I am taking 4 is there. So I can say that it is reflexive. Now we are going to verify whether it is antisymmetric or not. So if it is antisymmetric or not, if A related B is there and B related A will be there, then we are going to verify whether they are equal or not. So here A related B is there, and 1 is related to 2, 1 is related to 3, 1 is related to 4, 3 related 4, but there is no B related A. So A comma B belongs to R, but there is no B comma A belongs to R. So B comma A does not belong to, so obviously it is antisymmetric. If B comma A belongs to R, then we are going to verify whether A equal to B or not. If it is not there, then automatically we are considering it as antisymmetric. And the transitiveness, so here 1 will be there, 1 2 implies, so I am going to get 1 2, and the next 1 2 2 2 will be there, I am going to get 2 2, and 1 2 2 4 is there, 1 4 I am getting, 1 4 is also there, is also here. Then 1 3 3 3, 1 3 I am going to get, 3 3 3 4, 3 4 I am going to get. So subsequently I can get it is a transitive relation, then we are going to say that it is a partially ordered relation. So the relation is nothing but, what is that relation? So it is a relation, this relation is a partially ordered relation, and we can say that A comma R is a poset. Then to represent a poset, there are some represent diagrammatically any partially ordered relation. We are going to represent in a pictorial manner. That picture is known as a Hasse diagram. The picture is known as a Hasse diagram. So here in the Hasse diagram, three properties we are going to define in three different ways. One is reflexiveness. So reflexiveness, while we are going to represent suppose 1 is there and 1 is related to 1 itself, then I am going to write a self loop. So here the self loop is not required to mention because the partially ordered relation is reflexive. So there is no necessity to explicitly we mentioned a cycle. And the next another one is the antisymmetry. The antisymmetric is A related B we are going to mention, and there is no B related A here. So these we are not going to consider. Whenever A related B will be there, then A will be written at the bottom and B will be written at the top. So A, and I am going to write here, B I am going to write, and if I am going to mention a direction is there, then I am going to take it as A is this and B is this, then I am going to represent like this. So it is nothing but A related B. A related B. And another one is a transitiveness. Another one is a transitiveness. A related B and B related C. Suppose if it is there, there is no necessity to explicitly draw another edge from A to C. From A to C. It is automatically understood that by convention itself, we can say that the transitiveness is satisfied. So these conditions, any pictorial representation can be represented by using these. Then the picture is known as a Hasse diagram. Let us go for one example. A is 1, 2, 3, 4 and relation is a divisibility relation, and we are going to verify, and A, R is a partially ordered relation, and we are going to represent, then we are going to verify whether it is a poset or not. So for that, so divisibility relation, when we are going to take, what about the relationship is, the relation is x divides y. Here the meaning is x comma y means x divides y. X divides y. So here 1 divides 1, 1 divides 2, 1 divides 3. So 1 if I am taking, 1 divides itself, 1 divides 2, 1 divides 3, 1 divides 4. Similarly 2 if I am taking, 2 divides 2 and 2 does not divides 1. 2 divides 3, 2 divides 4. Similarly 3 divides 3, 3 divides 4, 3 does not divides 4. And whereas 4 divides 4 itself only. So now here the relation is, we are going to mention in that manner. This is the relation. Now we are going to verify this is a partially ordered relation or not. So this is reflexive because every element is divides itself. So it is a reflexive. And it is antisymmetric because A divides B will be there, but there is no B divides A. So 1 divides 4 will be there, but there is no 4 divides 1. So it is automatically understood, antisymmetric. And transitiveness is A divides B and B divides C. Automatically A divides C. So it is also transitiveness. So we can say that it is a partially ordered relation, and we are saying that it is a poset. Now let us go for the Hasse diagram for this. So 1 is divides 2 and 2 divides, 1 is divides 2 and 1 divides 3 and 2 divides 4. 2 divides 4. So here I am going to take it as 1 divides 3 and next 1 divides 2 and next 2 divides 4. Automatically 1 divides 4. So here I am not going to explicitly mention this ordered pair, this ordered pair, this ordered pair and this ordered pair, because it is itself reflexiveness, reflexive, so I am not going to mention. So 1 is related to 2, I mentioned here. 1 is related to 3, I mentioned here. 1 is related to 4 by transitiveness, because 2 is related to 4. There is no necessity for representing this. So I am going to, transitiveness is not necessary to represent and reflexiveness is not necessary to mention. So the pictorial manner, which is nothing but a Hasse diagram. So this is the Hasse diagram for the given partial order relation. Now here another one is possible positive divisors of 36. We are going to verify, we are going to write the Hasse diagram for this. So positive divisors of 36 means we are going to consider the integers which are divisible by 30, a number which is divides 36. So 1 divides 36. So I am going to write the set D. 36 is consisting 1, 2 divides 36, 3 divides 36, 4 divides 36, 6 divides 36, 9 divides, 5 does not divide, so 5 is not there, 6 divides, 7 does not divide, 8 does not divide, 9 divides, 10 does not divide, 11 does not divide, so 10, 11 is not there, 12 will be there, and 13, 14 does not divide 36, 13, 14 does not divide 36, so these two are not there, and remaining, so it is consisting the elements, the integers, the positive integers which are there, which divides the 36, all there up to 36 we are going to consider. So it is the set. Now we are going to verify that the relation D36 is the set and the divisibility relation is a partially ordered set or not. Partially ordered cities are not. So every element is divisible by itself. So automatically reflexiveness is over. And next, 1, suppose 2 divides 4, then there is no question of 4 divides 2. And say 3 divides 6, there is no question of 6 divides 3. So A related B will be there is no B related A. So antisymmetric will be there. So next, transitiveness, A divides B, B divides C, then automatically A divides C. Suppose 2 divides 4 and 4 divides 12, then automatically 2 divides 12. So there is no question of transitiveness. So transitiveness is automatically understood in the divisibility property. So we can say that this is reflexive as well as say antisymmetric and transitive. So we can say that this is a poset. This is a poset. So here, one is related to all the other elements of D36. So that should return at the below. When we are going to represent the Hasse diagram, it should be mentioned at the bottom. And the next 36 is related to itself. So that is written at the top. That will be mentioned at the top. Then 2 is related to 2, 4. That means 2 divides 2, 2 divides 4, 2 divides 6, 2 divides 12, 2 divides 18, 2 divides 36. And similarly 3 divides 3, 6, 9, 12, these numbers. 3 is divides this, 4 it divides this. And here we are going to mention. So here 2 and 3, they are not related to each other. So I am going to take it as in the next level 2, 3. Next level 2, 3. Now next level is 6. 6 is divides these numbers and 9 is there. So here 6 will be there and 9 is not going to be divisible by itself. And next another one is 36. 12 will be there. 12, 4. Sorry, I am taking 4 and another one is 6 and another one is 9. Another one is 9. So 4, 6, 9. These are not related to each other. So I am going to mention all these 3 at the next level. And the next another one is 12 and 18. They are not related to each other. So I am going to write at the next level. At the next level. Now I am going to write. So I am going to arrange the numbers. Arrange the numbers where 2 and 3 are not related to each other. 4, 6, 9, they are not related to each other. Not related to each other means they are not divides. So 4 does not divide 6, 4 does not divide 9. And similarly, there is no, these are two uncomparable elements. That is, there is no relationship. To 12, 18, there is no relation. And like this, so every level, we are going to find the elements which are not related. So those elements are going to be mentioned. And now, one is related to 2, one is related to 3, one is related to 4 and so on. So by transitiveness, one is related to all the elements of 36. And next 2 is related to 2 is related to 2 and 2 is related to 4, 2 is related to 6 and of course 2 is related to transitiveness 18 and 2 is related to 12 and 2 is related to 36 also in any way we can consider. Anyway, we can consider. And whereas 3, if I am considering, 3 is related to 6, 3 is related to 3, 3 is related to 6, and 3 is related to 9. Of course, by transitiveness, the above elements also related. By above elements also related. Now coming to 4, 4 is related to 4, and 4 is related to 12, and 4 is related to 36 by transitive itself. 6, if I am taking, 6 is related to 6, and 6 is related to 12, because 6 divides 12 and 6 divides 8 and next 6 divides 36 also. Now coming to 9 divides 9, 9 divides 18, 9 divides 36 automatically. Then 12 is divides itself, 18 divides itself and that divides 36 also. 36 also. So this is known as a Hasse diagram. This is known as a Hasse diagram. For the poset D36 comma, then the relation is a divisibility relation. So in the same way, we are going to consider divisors of 30. So, and now we are going to consider the Hasse diagram. For this is like this. So one is divides 1 divides 3, 1 divides 2, 1 divides 5, and of course by transitiveness 1 divides all. And similarly 3 divides 15, and next 3 divides 6, 3 divides 6, and of course 2 also divides 6. And next another one is, so 2 divides 10 also, 2 divides 10 also. Now coming to 5, 5 divides 10, and 5 divides 15, 5 divides 15. Whereas 15, if you are going to consider, 15 divides 30, and the next 10 divides 30, and of course 6 also divides 30, 6 also divides. So this is the Hasse diagram for the first one. And similarly for the second one is, so while we are going to considering the Hasse diagram, so here the 3 is related to 6, 12, 36 and 72. So it should be written at the bottom, and next 72 is related to itself, whereas 6 is related to 6 divides to 12 as well as 36. So I am going to write this is a 6 here, and next 12 will be there. 12 is going to be divisible by itself, and 12 is divided by 36, and 36 is also divisible by 72. Now we are going to construct a Hasse diagram for this. So we are going to get the Hasse diagram of this. This is nothing but a totally ordered set. That means any two elements, if you are going to consider from the set, either A related to B will be, they are going to be related. So this is having the Hasse diagram for the second one. This is nothing but 3, 6, 12, 36, 72. So with this, I am just concluding this, the descriptive questions or question banks in the second module. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.